I'm Giuseppe Maggiore. Welcome to the last lecture of the Introduction to C# course. Today we're going to talk about generics. Now, generics in general are built in order to allow us to define classes where some parts of our classes can host, store, or process different types in a way that is structurally richer, but also more complicated than polymorphism, because these types can be unrelated from each other. As usual, we're going to start by looking at how generics are used in C#. We will see how to store data in generic containers, such as list and dictionary from the standard library. Then we will look at immutable generic containers, also from the standard library. We will work a little bit with generic lambda functions. We will work with tasks, async and await in particular. Then, having seen all of these standard library usage of generics, we will write our own custom generic classes. Finally, we will take a look at a little pearl, so like a little cherry on top of this lesson. We will see covariance and contravariance in order to mark generic parameters as input or output in the way they are used by the class itself. Now, what's the point of generics? Now, some classes define algorithms or storage logic around specific containers. And a container, let's think about a box for now, is just a box. You can put things in it. You can put whatever you want in it. You can put an AirPods case in it. You can put a podcast microphone. You can put a plant in it. And the container just contains these things. So generics try to model this concept of a container, something that doesn't really care about its content. And the content in this case is the type. Containers in computing can be containers in the straightforward sense of I have an array and I put stuff in it. So a tuple is, in a sense, a container. But they can also be more sophisticated data structures. They can keep content sorted. They can keep it unique, so no duplicates. But they can also produce the content by means of calculation or through an API call. So they don't really contain their content, but they can fetch it on demand. This is actually pretty cool. Also, yeah, you could say the concept of it, I think, is very, very cool. All right. Now, let's start with some generic containers. The generic containers all exist in the system. Look, collections.generic. Yes, very good. And well, modern incarnations of the framework, like the one we're using now, do not really require such an include statement. So you might not see it in some samples, but you might also see it in older code bases. Okay. Now, let's start with the list. The list is perhaps the simplest such container. We can declare a list of int, and this will contain a bunch of integers. We can declare a list of strings, and this will contain a bunch of strings. And we can have a list of person, which hasn't been defined yet. So let's also define record person, string name, string surname, date, time, birthday. Yes, very good. There we are. Notice the syntax of list of the declaration. we have smaller than and greater than, but in this case you shouldn't see these two symbols as Boolean comparison operators, but rather you should see them as angle brackets. So list is not a class, so list itself, you can't declare something as list. This gives an error. It says, it requires one type argument. So this is even called an argument, this type that we're passing. So list is basically meta function, you could say, in our language, and you pass it as parameter a type, and you say, by calling the list meta function with a type, you say, okay, list, give me back the type of a list containing a bunch of integers. And by passing string, you say, okay, give me back the type of a list containing a bunch of strings, and so on. So basically, you call this meta function, you pass it a type, and what you require back, what you get back, because this function returns something, it returns the type generated on the fly for you. You could say optimized for storing the thing you just required to store. So a generic class, a generic container, is a meta function at the level of types that will create the desired type based on the type arguments that are given. You can actually take a look at this, and well, you can see the class is marked as list of the t, so we actually read this as, we say list of t because, well, it's a parameter, you know, and all of this code refers this t type. Yeah, but t is not known in advance, so that's why when you pass a t like int or string or person or whatever you want, then yeah, the rest of the code will basically, the type you put will replace t, and that will be created, and that new code will be compiled for you. And this also results in very fast and highly optimized code in this, indeed. And there is also some optimization, for example, depending on whether t is a value type or a reference type, in order to make the resulting class that is instantiated with the type argument faster. So there's quite a lot going on here. Even though we now have these three separate types, which are list of int, list of string, and list of person, and these three types are completely separated, like they are not polymorphic, they cannot be converted automatically, etc. They do share one so-called structural similarity. Any instance of list, be it list of int, list of string, list of person, has the same methods, has the same data, has the same underlying structure, and in general is used in the same way for any instance of the type t that we pass as an argument to the list. But that's it. Now, let's create instances of these lists. So we can say that the list of integers is a new list of int. Actually, let's turn this into var. And then, well, there's a very nice shortened syntax. Oh well, yeah, sure. 9, 10. Okay, very good. Let's restore. Yes, two spaces. We can do the same for the list of strings, of course. Oh, very nice. And we can also turn this into var. And finally, we can instantiate a new list of p of person. And well, let's go for the classic. John Doe, born in 1997. 5, 6. Oh, 5, 6. Very good. Let's also put another person. Jane Doe. And finally, Jimmy Doe. Oh, missing a comma. Yes. Very good. Now, what we have initialized are three lists the first with some numbers, the second with some strings, and the third with 3 instances of person. There are a series of methods that are also available. For example, well, I'm not going to show them all, but we have add. So you could say add 11 to the list. Then, well, we can clear the whole list. We can remove an element. Actually, let's take a look at some of these. Well, we have aggregate, all, any. These are really powerful. We're going to jump into those in a moment. We can turn it into a read-only collection. We can cast it down as an enumerable. We can calculate the average. If the list is sorted, we can perform a highly optimized binary search that every time cuts the list in twice. That's also a fun one. So, as you can see, the collection, the standard collection library is gigantic. And even though we cannot really show all of it, well, we can play a little bit with it, and get some possible inspiration. Okay, so let's start now by creating a list from range, enumerable.range. Yes. So together with the system collections generic namespace, the system link namespace is incredibly important because it contains all of the most interesting operations that we can perform on collections. Now, let me show you such an example. We can create a range, and the range goes, let's say, from 0 to 100. This is not yet a list, but we can convert it to list by saying dot to list. Okay. Now, given such a list, we can say, okay, I want to turn every element, so I have to pass a function here from int to whatever I want. Actually, let me show you the type of this. So this type is heavily generic because it works on any list. Actually, it works on any IEnumerable, which is the interface that lists all implement. And then we have a function from the element of the list to some new type, which is called the selector. And the function will be applied on every element of the source collection, and the resulting collection will be created. So we can say select x goes into x plus 1. And then we have to convert to list again. And what's happened is that we now have incremented all the elements by 1. If you wish to see this, of course. Now we start with the list 0 to 99. We take a step. Oh yes, the debugger is actually stopping inside the little lambda. Let's go to the end of this whole sort of loop, and there you go. Now every element has been incremented by 1. This sort of declarative programming technique produces a very powerful alternative to, offers a very powerful alternative to loops. There was an estimate made by John Carmack, the sort of rockstar developer who built Quake, Doom, and these games, and he's absolutely a brilliant programmer. And he estimated that in the code base of those engines, which are very large code bases, more than 80% of the loops were no more than this kind of simple transformation of all the elements of a collection at the same time, for example, or a filtering. So yes, these things make it a lot easier to recognize an iteration structure and to standardize your iteration structures. Now, next to select, we also have the possibility to filter. So we could say we want to filter only the elements for which this lambda returns true, for which this function returns true. So instead of 100 elements, 0 through 99, we will have the even elements, 0 through 98. And let's see, 0, 2, 4, 6, 8, and the last one is, let's click through, 98. Yes, very good, very good. Of course, we can combine these operations, so we could select and say, first we increment, and then we take only the resulting even elements. So this means that we had 0 to 99, but we've incremented, so now we shifted everything back by 1, so now we have 1 to 100, but then we filter and then we keep the even elements starting from 2 to 100, extremes included. Let's take a look. And you can see we start at 2, not at 0, because we shifted by 1, and we end at 100 instead of 98. One funny thing about select is that it can also change the type. So let's have a new collection, and we say that for every integer, we create a new person, and the person will have, let's say, a sequential name. So John X, Doe, and the date time. No, but for now let's put the same date. But no, actually we could say that the months are the months are sequential. So we could say x modulus 12. I think it's +1 though, because the dates start at 1. Well, we'll see in a moment if it crashes. Well, it doesn't crash, so that is good. And now we have John 18, John 19, born. Okay, looks like it makes sense. And you can see that the months are sequential, 9, 10, 11. Okay, very good. The combination of a range and then a select in order to transfer. So the range initializes the collection with numbers, and then we select right away to create something richer. Is one of the best ways actually to mock a data structure and to control how many elements we are creating based on some based on the index of the element that we're creating. This is actually quite powerful. Given a list, we can sort of treat it like an array, but also not quite, because yeah, a list is like an array, but it's dynamic. We can add elements to it, like we've seen. We can call new collection.add, and this will simply add an element. We cannot add an element to an array, and internally a list uses still uses arrays for storage, so it's pretty fast. We can look up elements in a list. We can say that we want the first element with the usual lookup syntax and the index of 0. We can look up the last element with the same lookup syntax of the square brackets and the little hat1 syntax, so saying one element before dot length, or dot length minus, and then 1. Let's no, we don't need to run this with the debugger actually. And what do we get? Well, we get John 0, that will be the first, and we get John 99. All right. We can reassign values. So let's say that we want to reassign the value of new collection of 1 as new collection of new collection of last with, this is a record, and let's say the birthday will be new collection 1 dot birthday plus time span from days. Okay, now what we're saying is that the last element of new collection is a copy of the last element of new collection where the birthday is the same birthday plus 1 day. Let's see how this behaves. So the last element, all right, here we are, 4/2/1995. Okay, very good. Let's take a step, and 4/3/1995. Okay, very good. Well, this also seems to work. Excellent. We can show, of course, the count, so how many elements do we have, etc. I would advise to start playing with most of these with most of these operators. Like, for example, we can ask whether or not an element exists with a given match. So the match is a function, a predicate that takes as input a person and has to return a boolean. So you could say, is there one where the birthday month is 3? And I'm kind of guessing that we're going to get a yes here. So we get true, yes, makes sense. But is there one whose birthday is on the 13th month? And of course, this is false because this cannot happen. So manipulating collections in C# is done with this link library. The things that you will see in the list library, if you include the link namespace, are gigantic. It's like so many methods, all, any, average, select, where, join, order by, then by, so many things. And they are actually one of the things that have been beloved in C# for yeah, a decade and a half now. So it's really worth playing around with it a little bit. We are going to have a whole course on the topic of link and the connection between link and databases, so don't worry. But for now, indeed, I would encourage you to play around with it. The last one I wanted to show, though, is binary search. So let's say that we have a series of random numbers. So we create our integers. And there's 100 integers. Now for each integer, I extract a random value. Let's run this with the debugger. And you can clearly see this is pretty random. Now, let's make this a little bit more disciplined. How many random values? Let's say that we want, well, we do want a reasonable amount. Okay. So, how many random values? And to next, I will also pass the same parameters so that we get values between 0 and 1 million. Otherwise, the limit is 2 billion in both directions, and that's a little bit too sparse. Then the chance of a hit is basically 0. Okay, so now it's a million values between 0 and a million. It's a million, right? Let's look at the zeros. Yes, it is a million. Okay, now for a series of times, we will look for a random value between 0 and 1 million. And let's see how long this takes. How many searches? Let's say that we do this 1,000 times. And now for I is 0 to how many searches? Just count the number of searches. Then we check integers dot, well, there is find for exists. it doesn't matter that much, exists a value that is equal to, let's say, searched, and this will be a random number between 0, of course, and how many random values, because this is the range. And we check whether or not this one exists. Oh, of course. So we look for the one element that is equal to searched. Let's time this. So we create a new stopwatch. We end the stopwatch, of course. We stop it. And when we're done, we print how long this took in milliseconds. Okay. Now the this is taking its sweet time. It's 1.6 seconds. Now what is exists doing? Exists is going through all the elements of the list one by one and checking whether or not this predicate is matched. Okay, I mean it's not forbidden. But now what we're going to do before converting this to list is we're going to order. And we're going to order the sequence in ascending order. So if we take a look at the list now, you will notice that it is sorted. And the sorting is super optimized. Now you can see first smaller values, and they grow, and they grow, and they grow, etc. Okay, very good. Now, instead of running exists here, we are going to perform a binary search. And we're going to search, and we're going to search the searched item. Let's see what happens now. 0 milliseconds. Even though I'm cheating a little bit. I'm cheating a little bit. So I'm going to uncheat this application. So let's reassign the integers here so that we order and perform to list, and let's also count how long this takes, because binary search only works with an ordered list. Okay, so 269. This is a little bit more fair, even though we should decide whether or not we count or discount the ordering, because the ordering takes time. So let me explain very quickly what just happened, because exists, what it does is it goes through all the elements. If you have 1,000,000 elements, you have to take 1,000,000 steps. If you have a billion elements, you have to take 1,000,000,000 steps. And every one of these steps has to be taken, in the worst case, of course, if the searched item is not there, that's the worst case, for every search that you need to do. Binary search does something incredibly smart. So let's say that we have 10 elements, and we're looking for element 7. Then what binary search basically does is it takes the middle element. Let's say the middle element is 4, and because the list is ordered, it checks if 7 is bigger than the middle element or smaller, and depending on that, it cuts the list in two and only looks in the right half. And so what's happening here is that well, all of these elements are being discarded because the middle element is smaller than the one we're looking for. So the elements that are smaller than the middle element can be discarded. And yeah, okay, now let's say that we also have 10, so let's make it a little bit more challenging, that we have another step. Now in this case, let's say we take 8 as middle element, because we have 2, so we have to pick 1. And 8 is bigger, so we can refocus the search on the smaller elements. Now we have 6, and 6 is smaller, so again we focused. And we had 11 elements, and it took 4 steps. But let's say we have 1,000,000 elements. Okay. Then at the next step, we just divide by 2. And at the next step, we divide by 2. And at the next step, we also divide by 2, and so on. You can see how much smaller this thing is going, how quickly this thing is getting smaller. So the next step is going to be 60,000. Okay, approximately. The next step is going to be 30,000, then 15,000, and you might wonder, okay, but where are you showing all of this? Yeah, very simply, because binary search is such a ridiculously faster way of going through an array that I believe everyone should be always aware of the power of the algorithms that we can use to speed up our applications. And look, so we went from 1 million items candidate to 1800 in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps. So in 10 steps, we have reduced this by a factor of 1,000, and then it takes very little steps, because you could say, okay, divide it by 2, you have 900 elements, 450, I'm approximating 225, and yeah, now we're basically done, 110, etc. So with something like 30 steps, no, not even 20 steps probably, you go from 1 million items to an answer, to a definitive answer. So these data structures also offer these very neat optimized algorithms that are super useful and can greatly accelerate our performance. There's also going to be a course on this later on. It's going to be a course on optimized data structures and algorithms. It's going to be a lot of fun. Lists are basically just arrays with a few extra capabilities. Specifically, a list can be extended by adding elements to its end with methods like add. And so basically they are arrays that can grow. But for the rest, there is no difference between lists and arrays. Let's introduce one of the most powerful, flexible, useful, unmissable data structures now from the System Collections generic library: dictionaries. Dictionaries, which in some languages and contexts are also called maps, are key value containers. So the contents are the values. The contents would be the things that you would also put in the equivalent array. But the values can be accessed by means of a specific key. You could imagine an array to already be a sort of key value container where the elements of the array are indexed by the key, which is the position, which is an integer. In the case of dictionaries, though, we can have any kind of value. Okay, that's the same as arrays or lists, but also any type of key we want. So, and usually the key is a unique identifier. Well, usually the key has to be a unique identifier, because for the dictionary the key has to be unique, and it has to be unique with respect to the value. It's very common to actually have an ID, for example, the ID in the database, and that can be a numeric ID. A GUID has some very strong security advantages, etc. As long as the key is unique, though, it can also be an email, can be the combination of name, surname, age of the user, which is not really unique, so that would be dangerous. As long as you're sure it's going to be unique, it doesn't matter what it is. So let's consider a custom data type. Let's say something that could come from a database. So this would be the job record, and a job has a GUID, the ID, the name, and the salary. Let's be materialistic here. Okay, now what is a GUID? A GUID is one of these collections of, you know what, I can actually show you what a GUID looks like. So console.writeLine. This is something I wish I had been taught earlier, to be honest. Okay, so GUID, new GUID. So we just get a new one, and let's just run this little program. Go. Okay, and well, this is what a GUID looks like. And look what happens if I run the program again. Or better yet, let me generate a bunch of GUIDs. That's also good. So for I from 0 to, let's say, 10, we just print a bunch of GUIDs. There you go. Now, the U of GUID stands for unique, and the ID stands for identifier. GUIDs are all unique. They are generated based on a mix of the current timestamp, characteristics of the CPU, the physical machine, etc. So that it's guaranteed that whenever we call new GUID twice, the result will always be 2 different GUIDs. And the very cool thing is that GUIDs are not really sequential, so they are quite chaotic. So there's no way of predicting that if this was the previous GUID, then this is going to be the next one that is generated. So very often in simple database structures, you will see IDs that identify the records of a table uniquely, and those are integers. But if you log in and you see, for example, on the URL that you're logged in as user 10, then you know there's probably users 0 through 9, and you can also look for user 11, 12, etc. And so you might try to brute force to perform brute force attacks that guess users just based on their ID. GUIDs, on the other hand, are unguessable. You can actually use GUIDs as a basis of scrambled URLs that no one is going to be able to guess. So GUIDs are, in general, much better and much safer and unguessable than integers as IDs. So that's the reason why the record job doesn't have an int ID like I just adjusted, but a GUID ID. Very good. Enough. We're talking about dictionaries, and in dictionaries it's very important the choice of identifier that we make, and GUIDs are in general the best, let's say, baseline standard identifier. Alright, now let's create a bunch of jobs. So the jobs will be a new dictionary of, very close actually, string job, but of course it's GUID job. Now, what does this mean? This means that every entry of the dictionary will have a GUID connected to a job. As it stands now, I'm not really imposing in any way that the GUID and the ID of the job are the same, but it does stand to reason that this is what we're going to do. Okay, then I'm going to define a tiny little function that is add job to guarantee this. Now it says GUID job ID job. No, that would be wrong. It will just be the job. And what will add job do? Okay, that's close enough. So we take the job ID and we connect it to the job. Why is it complaining? Oh, because it could be null. No, this will definitely not do. This thing will never be null. Okay, and then we can simplify this, if I'm not wrong. Yes, indeed. By the way, so what just happened? Let me dive into this. So the latest version of C# has this little question mark next to types to signify that, okay, jobs can be null. And now it's complaining that I'm not doing any null check because, well, I'm doing jobs.add, but what if jobs is null? That's a fair concern. So what I'm doing is I'm declaring jobs. So by default, it had the question mark. We can actually see it here. It says that this is a dictionary. Oh my god, what a mouthful. Look, dictionary t-key value, where t-key is not, yeah, okay, this is unreadable. Let's see if okay, this is better. It's saying dictionary of GUID job question mark. So it's assuming by default it's nullable. So what I have to do is I have to state specifically no. I never want to be able to put null here. So if I try to say this is a new dictionary, that's fine. So I'm recreating a dictionary. This is acceptable. But if I try to put null, then I get a warning. These warnings will again become errors in later version of C#. You can bet your dog on it. Okay, but now if you look at this, statement, it's kind of ugly because before we had var, and var saved us from the repetition of the type in declaration, and then the call to the constructor, blah blah blah. This is kind of ugly. But in C# when the type is known from the declaration, you can just call new, and this will invoke the appropriate constructor of the type you declared with. And this is actually very nice because when Vard can't do the job right for you, then at least this still saves you from some repetition. And I have to say, new and then just the brackets looks kind of naked in its own way, but it's also kind of, it has its own streamlined sexiness, you know? Okay, anyway, I digress now. Let's go add a job, and here I can simply say new job, and then GUID dot new GUID, and then okay, what's this job going to be? It's a software developer, and it's going to be it really depends on the market, but let's say 48,000 gross per year. Maybe reasonable for a junior media developer in the Dutch market. Then new GUID, teacher. And the teacher, well, we do know teachers are not paid much, and that is also true, unfortunately, in our little example. And then the king of kings, the plumber, who makes a whopping 113,000 a year, leading the other two guys wondering why did they spend so much studying when they should have just gone and become a plumber. Just kidding. Anyway, we can now do stuff with our dictionary. The most the most common thing we can do with the dictionary is quite simply to put between square brackets a GUID. Now, unfortunately, I don't really know my GUIDs, so I'm going to just save them in temporary variables, and then we can play with them. So let's say J1 is new GUID. And here we put J1, and then here this will be J2, of course, and then J2, and finally J3, and this is J3. Okay, then at least we know we saved those values in temporary variables. In normal situations, of course, you would have places where you render for example, a job on a, I don't know, web page or a desktop application, etc. And so you have the GUID in a variable where it comes from, or maybe it comes from a relation. So you have the person, and the person has a job, and so inside the person you have the job ID that points to the job, etc. So in general you have it, but in our contrived example we do not, so we have to save it explicitly. Okay. So now we can say jobs of J1. Okay, and let's take a look at what the debugger says about jobs of J1. We always add the empty statement so that I can just let the debugger stop at that last empty right line statement. Oh, that's rather unfortunate. Oh well, you know what? I'm going to show it in a different way because J is a record, so we can just print it to the console. Let's, oh, not watch run, we just run this. And off we go. Well, of course it has been found, and if we bothered to also print J1, which is an interesting exercise by the way, well, of course, because of the way our program is constructed, J1 and the ID of the job printed will of course be the same, D0, B61, D0, B61, and that's very good. We'll do the same for J2, and of course J2 is also going to be available. And look, it's kind of nice because it looks like we're looking up elements of an array, but actually it's a much richer data structure. And okay, so also the same clearly, and so on. Now let's try to get something from, let's say, the empty GUID, which I think is all zeros. And okay, what happens is that we get an unhandled exception, which is system collections generic key not found exception. The given key and then the empty key was not present in the dictionary. When dealing with dictionaries, you will get this, which is very similar to the out of bounds exception in arrays when you try to read an element which is an index which is simply not there, like an index beyond the end of the array. That's life. There are languages, notably for example JavaScript, that are really, you could say, built with the philosophy of, you know what, let's just try to continue and hope that maybe another piece of the page at least remains visible, this piece of the page is doomed, and so looking up elements that are not there gives you back a value like undefined, which is the alternative to null. So null means it's a legitimate value but without data, whereas undefined in JavaScript means no, it's nothing, it's nothingness, it's absence, which is to an extent a bit silly. C# is a bit more structured, you know, like German policeman. So, and C# rather errors out and stops the flow. It's a backend language, it's built for transactions, it's built for reliability, so we really get why it makes sense to say no, you don't get a value. Okay, so how do we cope with looking for values that might be there? Well, for example, we should check contains key. So we could say if jobs contains key, and then, well, we're looking for empty, so we leave it. And if that's the case, then we can actually look up the job based on this GUID that we're looking for. But let's actually generalize this. So search ID, and this will be a GUID empty. And there you go. But of course, nothing will be printed. Just put an else and saying, okay, the key was not found, but you get the gist, because contains key has returned false, and it's actually a good idea to first, or always a good idea to first call contains key, and only then to make sure that you look into the array. Now, I would like to also open up an interesting little node, a little side node about mutability and immutability. Now, suppose that you had another thread running that modifies the jobs. And so you have contains key, and then the other thread runs an instruction that, oh, what do you know, removes this key from the dictionary. So because jobs is a shared mutable variable, if it changes in the other thread, then between lines 17 and 18, the condition of line 17, that is the key is contained in jobs, will not be valid anymore. That's why we will look at the immutable alternative to this, which is safe when doing concurrent operations on multiple threads on the same machine. But in general, you will see this kind of defensive code very often, and that's very good because this is good code. There's plenty of more methods. Let me see. Oh, you can also check contains value. But interestingly enough, how is a dictionary organized? Dictionaries are organized by creating a search tree or a hash tree. I don't know actually exactly which one of the two, but in any case, a super mega quick data structure that allows us to answer these two questions. Is a key present in the dictionary? And give me the value corresponding to this key as quickly as possible. Remember the binary search examples we just saw? Basically, dictionaries are optimized for the same kind of performance of the binary search. The algorithm is basically the same as binary search, conceptually at least, but only for the keys. So when you see something like contains value, well, remember that contains key is going to be fast, contains value is absolutely not going to be anywhere near fast. Yeah, you can get the enumerable of all keys, so you can go through all the keys. You can get the maximum value, the minimum value. You can order, you can remove items. Removal of course makes sense, and removal is, as you guessed, by key. So you remove a key, you don't remove a value. And so on. I mean, we can't really look at all of this. I don't think it's going to stick to anyone's memory, but I like to just give you an impression of this thing is gigantic. So many options. Okay. Oh, this is kind of funny because try get value is, let's say, the safe variant of the if job contains key. So basically, what you can do is I'm not entirely sure. I'm not entirely sure I like this, but okay, this is in just one instruction, so it's yeah, okay. So what's happening here? This says, okay, try and get the value corresponding to this key. And this returns true or false. It returns true if the value has been found, and it returns false if the value, if the key has been found, and it returns false if the key has not been found. And what is this monstrosity? Well, this monstrosity is, okay, so varj declares a new variable, which we also mark as an output variable. So because this is immutable, you can't really reassign a variable that you pass to a function, because a function gets as parameter a copy of the variable. But by marking it as out, we're basically giving try_get_value the power to modify this variable j that we declared here, so that even after the function is ended, then this is basically a second return value. It's a bit of an old construction. You actually see it here, this modifier. You can actually use it in your own functions when you want a function to be able to modify a parameter and not therefore get a copy of the parameter, but literally just the parameter itself, or better, a reference to whatever type the parameter gave you. And it's also kind of cute because it's annotated. You can see that C# is trying to get safer and safer and safer in this declarative way. It says, well, this might be null, or at least it will be the default value, which is null for references or 0 for integers, etc., when the return value of try_get_value is false. Kind of funny, but there are better ways to do this. And they will come out in C# eventually by returning a proper union of, like we saw in the previous lesson actually, by returning something that is either a result, a record, or an error, and then you get always something back, and you have to check whether or not the result you got is the error with the switch expression. But dictionaries are much older than the switch expression, so it makes sense that the language is sort of still equalizing itself in tiny little steps. We can also iterate a dictionary. And what happens? What is the iteration variable? Well, now this is in the I want to type job. Yes, okay. Job is a key value container. So it has the key, which is the identifier, and it has the value. In our case, because we know that by the way we fill up the dictionary, the value.id is always going to be able to the key. Well, this is a bit redundant, but in most cases it isn't. And now we could print the whole dictionary, for example, by saying the following. We could say job.key points at job.value, or let's say job.value dot, and then we can just get the name. And what's wrong here? Oh, of course, the closing quote. And I can see this is the ID for developer, this is the ID for teacher, this is the ID for plumber. We can also write values. For example, let's print here the whole job.value. And let's say that we've decided that, okay, teachers have to earn a little bit more. No, wait a second. This is a video for developers. So let's say that we've decided to raise the salary of developers by a very reasonable 200%, because software developers are building the infrastructure, the digital infrastructure of the future, and we are very, very important people, and we should be paid a lot. So we print all the jobs, but then, in order to see the difference, we take jobs of J1, and we say jobs of J1 is equal to jobs of J1 with salary is jobs of J1 dot salary times 2. All right, let's run this, and you can see that developer was 48,000, but now it's 96,000. Okay, plumbers still eat our lunch, but the difference is getting closer. Okay, very good. There is a couple of notes to be made here. So basically we're reading jobs of J1 1, 2, 3 times. So the concurrency warning I shared with you It's now even worse. And really, this thing about concurrency, yeah, okay, you're learning C# and you're wondering, okay, I'm at the beginning, or why is the dude talking about concurrency? I get it, but the point is not to get to the level where you can write a very fancy hello world. The point is to get to building, you know, the cool hardcore stuff. And so you have to find out right away what it takes to be one of the champions. All right. So concurrency is a serious is a very serious thing. All right. But before we jump actually into the into the next bit, I would like to show you the big difference between dictionaries and lists. It's actually a very, because I said, okay, it's very fast, but what does very fast mean? And I really want you to have a proper feel for this. Now, okay, let's create a list now of just a bunch of integers. So this will be the list, and we just, no, Rosalind, we don't, this is not required, okay. And then let's have a dictionary, and the dictionary will contain, well, okay, you guessed correctly, and the dictionary will just be an int connected to the same int. So basically, we're just checking how fast the key lookup operation is, what value we carry along, we don't really care about. Okay, cool. Now, let's put in a lot of values. How many? Well, none values, just a lot. Okay, and of course, how many search lookups will we have? Will be also a nice round number. Okay, so for each value, okay, then what do? We add the value to the list. Oh, something horribly wrong here. And also we add to the dictionary the value as both key and value. So the I as both key and value. Okay, now for every lookup, so for all the lookups, we get a random value and we search for it. Why random? Because yeah, I don't want to know. I want to do a chaotic search like in real life. You don't know which elements are going to be looked for by the user or by the dynamic situations that arise in our program. Okay, so searched will be r.next. And most of these lookups will just not work. And then we say l.find. And what are we looking for? Well, we're looking for a value that is equal to searched. Okay, not even bothering to give a name to this sort of internal iterator. That's cool. Okay, and obviously we do the same for the dictionary, but we call dictionary.contains key of searched. Okay, let's create a stopwatch, and here we stop the stopwatch and print how long it took to look for 10,000 values in a list of 100,000. So sw.elapsed milliseconds. Then what we do, of course, we restart the stopwatch. Actually, there is a restart method in the stopwatch, but I'm kind of suspicious, so I'd rather start from scratch, create a new stopwatch. Okay, let's run this, and okay, it's thinking. Oh, when it's thinking, okay, boom, my God. So there's a difference of, so basically the list is 1,000 times slower. But that's not really true actually, because let's say that we were to look for twice as many values. Let's see what happens. Okay, so this was 2.5 seconds versus 1 millisecond. Okay, look what happened. We doubled the number of searches, and because every search in the list has to go through the whole list, and in most cases we're looking for random values, so they will not be found, so we have to get to the end of the list, yeah, then twice as many searches results in roughly twice as much time. It's actually quite precise. There's a difference of a few milliseconds. Okay. How? The dictionary still takes the same amount of time. Well, it takes a tiny little bit more, but there's this difference that in the list you double the amount of operations and it doubles the time. But in the and also obviously if you double the size, well, you will see exactly the same. And it's also interesting. So you double the size, and then well, the list also still doubles, and you would expect really the dictionary to become much worse, but no, the dictionary stays there. So we say that the list search grows linearly. So you double, it doubles, you triple, it triples, etc. You triple the size, it triples the time, you quadruple the size, you quadruple the time, etc. But the dictionary, because it cleaves the search space into every time, it's logarithmic. So you double the size, but you don't double the time it takes to search for it, because it's just one extra step and not, yeah, twice as many. And this is fascinating. We will really dive into this in the algorithms and data structures course. But look, this is just a desktop machine bought in a store. This is incredible. But imagine if you had to do this and you're, I don't know, hosting on the cloud, you're hosting on Azure, you're hosting on Amazon, and yeah, all of a sudden you build a data structure that your users that requires your users to wait longer for operations. So that's already annoying for your users. So yeah, that's already -1. And you have to pay a lot more because the CPU that you use from the cloud is rented, and you basically pay per CPU cycle. So there you go. So you build software that's worse, users are less happy, and that's a lot more expensive to run. So knowledge of optimizations and using dictionaries as much as possible strategically can have an insane impact on how fast and good your applications are. Of course, we can combine these data structures in all sorts of ways. So let's take a look. So there is not really one size fits all, and so we can join things together. Because there is no one size fits all container that can solve any containment requirement of any program forever, it is possible to use the principle of composition and use multiple containers in a nested configuration. There is no limitation whatsoever to how much we can nest in order to accommodate the needs of the data structures we must represent. The nesting can happen in multiple ways. One is very explicit and the other is implicit, but also actually very important. Let me give a little kick to the IDE. The IntelliSense seems to be a bit borked. I think it's better now. Whatever. Okay, so we could say that we have a dictionary of list values. And this is an example of, this is a clear example of nesting and composition. And if we want to make it, a little bit more realistic, we could say that, well, we could have a dictionary that for each, let's say that for each postcode, in many countries, a postcode connects to multiple houses, and indeed from one postcode to many houses at the same time. And then we could have postcode, I don't know, could be string letters, and then a string, or sorry, the numbers followed by some letters, whatever, doesn't really matter. And then of course for the house we could have, yeah, I mean, whatever we want, let's say blah blah blah. Okay. Another way of doing nesting is perhaps as common, probably even more common than this, is when things happen implicitly. So let's say that we have a dictionary of, let me think, a dictionary of, let's call this D2. No, let's keep it abstract for now. So from int to a data structure, to a given record, let's even call it R, doesn't matter at all. And then we have a record R, no, just R, and inside the record we have a list, and this one I'm calling L. Now this pattern is super common, so what this pattern looks like is basically you have a dictionary, or you have this can also be flipped around, of course. You have a list, you can have a list of dictionaries, etc. We have in this case a dictionary of just plain records, but inside each and every one of these records, what do we have? We have a list. So we have nesting, but this nesting is slightly less explicit than the one we just saw. So, but still it is nesting because now we have a list inside inside the dictionary. Something that is actually quite common is to have dictionaries inside dictionaries. So this setup of the postcode makes it easier to find houses by postcode. So basically, this thing that we're building here, which I could also rename to something slightly better. So, for example, houses by postcode. Yes, there you go. Are fast. These houses by postcode are fast to find. Are indexed, you could also say, by their postcode. Okay. But suppose that in our domain we want to be able to search first by postcode and then by, let's say, square meters. And then in the house we would have the square meters. Okay, very good. But yeah, then given the list of houses at the postcode, finding a house with a given with a given square meter, that might take some time. So we could nest the dictionary again. We could say that now, first we have a dictionary by postcode, and for every postcode we have a dictionary by square meters of the list of houses. And let's say that this is, for example, a big flat house, a big building with a lot of flats with different square meters, then yeah, it would actually make sense. And this would also be a list, because in a big flat house, a lot of the apartments would have the same size. And the proper name would be houses by postcode, then square meters, so that it is very clear that yes, indeed, we're dealing with houses that are sorted first by postcode, then square meters. Okay. And well, we could wonder, okay, how do we search in this? So let's say that we want to find we want to print all the houses by postcode and a range of size, because the square meters, you don't necessarily want to say I want all the houses with of 90 square meters, but between 75 and 105 square meters. So print all houses with let's say search houses. The parameters will make this clear. And then we get a postcode, and we get min square meters, and we also get the max square meters. Okay, very good. So how do we do this? Well, the search by postcode is ridiculously simple, because we just look up these houses by postcode than square meters. So this would be yeah, I'm just going to call it houses, or because it's a temporary variable. Otherwise, this would be houses in the postcode or whatever. Now, well, we have to go from min square meters to max square meters inclusive, so it's greater equal, even though I have the pretty ligature font that shows it as a single character. And now I have to get all the houses. So let's say for each close enough var house in houses of I, because I is the current amount of square meters, and so houses of I. This you could also see as but there's no reason to repeat this expression because this still takes a little bit of time, but this means first the dictionary of houses by postcode, and then we look up the houses with I square meters. I'm not a huge fan, honestly, of names like I for something like this, so when it's the index in an array, I can live with I, j, etc. But when it's something more expressive, I'd rather have a name that properly reflects this. Okay, cool. And but then we can do something with house. For example, console.writeLine, and then we just print the house. Okay. Now the dictionary is empty, and well, we have to now. We have to fill up the dictionary, so new postcode, and well, 1, 2, 3, 4, AB, and then we create the new dictionary. It's actually very handy to be able to create dictionaries like this. Let me check if it's happy. Yes, it looks happy. Okay. Then the dictionary to the right, of course, we need to initialize it. So square meters. Well, let's say we have got 75 square meters, and now we need a list of houses. So new house of, yeah, okay, that's actually kind of on the boring side of oh, pardon. Well, this is going to be a list, and because C# knows that it's a list, I don't really need to put a lot of information. No, let's actually give names to the houses. The square meters are implicit, so string name, yes. Or just a sort of identifier, so this would be a house. 75 1, so the first house with 75 square meters, then we can actually debug, 75 2, 75 3. It's always good to make sure that the code you're dealing with and the examples you're giving yourself are debuggable. This is something that this is almost a lost art. Okay, so we have 3 houses with 75 square meters. Add the same. Oh, well, absolutely not done. Let's also make sure that there is at least another entry for 105. Okay, and these are the 105 square meter houses. 105, very good. And then let's create another postcode, and the structure will be the same. 5, 6, 7, 8, AB, very good, and then 75, 105. Now this I would argue is a decent testing structure. Oh, I seem to have missed something. Okay, we'll look into it. But at least we have no empty list or no list with just one element, because we want to always test plurality. We want to always test the fact that there's multiple stuff in our data structures, and the same applies to the inner dictionary at the nested level and also to the outer dictionary. Okay. And now something is okay, so int list houses. We're not happy about this. Well, the structure of this would be curly brackets, but what about without this? Is it happier? No, it's still quite unhappy. No, this is the list. This is the nested dictionary. Of course, each one of these entries, being a dictionary, is supposed to also be a tuple. So We're drowning in curly brackets. Very good. Okay, so let's see what happened. So these are the external curly brackets of the dictionary. So in here go all the key and values, and the keys and values are separate, are within a curly bracket block, which is now the one I just selected. So these are the curly brackets of the key and the value. Here is the key, then a comma, of course, and here is the value, which is the nested dictionary. Okay, here are the curly brackets of the nested dictionary. And every entry of the nested dictionary is, between curly brackets, a key and a value. The value is a list, and because it's a list, it has curly brackets with all the values of the list inside. Okay, so now you can see that the error here is that the curly brackets of the nested dictionary do not contain key value pairs with curly brackets on their own. But this is now fixed. Oh my god, this is horrible curly brackets. Okay, anyway. Now we can say search houses and well, which postcode? Postcode of 1, 2, 3, 4 AB. Now I just know, and let's say that we want to be between 70 and 80 square meters. Okay. But I notice we have made a mistake in our test data because the names of the houses are not expressive enough. So let's fix this. I'm going to add the postcode because we want to see with our test data, given that we're testing our ability to query by postcode and by square numbers, by square meters, we must be able, given a house, to see immediately that yes, we are getting the right one. And this requires careful test data. I've seen people waste so much time on test data which doesn't help with actual debugging, you know, so often. All right, now, oh, is this, oh no, not .NET Watch run, but rather .NET Watch build. And then we run this, and boom, something is going to break. And what breaks? The given key 70 was not present in the dictionary. So before performing this lookup of the square meters, we are supposed to check if houses contains key square meters. Because if it doesn't, well, we don't get a proper value here. We get an exception. Okay, now we looked for 1, 2, 3, 4 AB, so the postcode is correct. And we want it between 70 and 80. Okay, very good. Let's say between 70 and 150. Now we get all of them. Let's say between 100 and 150. And there we go. Let's change the postcode. And it also looks like it's working. Now we've tested, and I think it's also important for you to see this, we've tested all the variations. We've tested enough of, we turned around this little cube of the search space, and from many perspectives it looks like it works properly. So now we can be relatively safely assured that this thing works in general. Okay. Something that's actually very cool that we could have done is also return a list of all the items that, of all the houses. And you can imagine we could have said that this thing returns a list of house, then we create the result, and this is a list of house. And then for every house, instead of printing it on the console, which is kind of ugly, result.add house, and at the end return result. Okay, so now search houses, and then we could have, you know, for each var house in search houses, and we can decide what we're going to do with this house. Oh, let me be super lazy. Yes, haha, I saved myself from pressing 20 keys. Okay. Obviously, it's a lot better to return something like, oh yes, to return something like a list of results rather than just arbitrarily deciding, hey, we're going to print all the results, because that's what the user certainly wants. No, that's most certainly not what the user of your library needs from you. Okay, very good. But let me show you something very, very, very cool. We can also say that we return an IEnumerable. Nothing breaks, everything still works. What is IEnumerable? IEnumerable is an interface that is inherited by dictionary, by list, by array, by basically every data structure that you can enumerate. And what is enumerate? Well, enumerate is very literally run a for each. That's kind of it. An insanely cool sort of enumerable that you can build is the lazy or implicit IEnumerable with yield return. So instead of creating the list here, which takes memory and you put stuff in it, there is a special combination of keywords which is yield return. Okay, this is kind of like magic, and that's it. So what does this do? This will, well, first of all, work exactly the same. There you go. But basically, we are building, this is what is also called a generator. This will create a little state machine actually that implements IEnumerable, and whenever you say, hey, give me the next element, it executes this code, lines 18 through 22, until it reaches a yield return statement. And then it just, boom, gives you back the next house, the next item. When the last line of code is reached, then the enumerable says, I'm done. It signals its end. So basically what you've created is just the same collection, but without allocating any memory. Because, well, we already have the code that can calculate the collection on the fly. So we make the collection get calculated as it is iterated. This is actually like ridiculously cool.
As you write more and more code, then you will discover why a lot of developers, especially as they grow in seniority and they have a lot of lines of code behind their back, dislike mutability. Mutability and side effects compromise the readability and integrity of code. And whenever we try to understand a piece of code that is very heavy in mutations, then you have to think about, okay, so this variable becomes 3 when that other process is doing this, but it becomes 4 when that other process is doing that, but also that second variable has this relationship, etc. It's very difficult to track these very complicated dynamic relations between mutable variables and different parts of the application across time. So for this reason, mutation is often shunned upon, and there are many immutable libraries that try to just get rid of mutation altogether by offering data structures or frameworks that disallow mutability altogether. When it comes to containers, we have the immutable collections.net that are designed exactly for this purpose. Interestingly enough, originally the system collections generic framework was fully standard library was fully mutable. Then a NuGet package from Microsoft, the same collections generic but immutable, became quite popular, and since I don't know how many years, it's part of the .NET framework as just one of the standard libraries. So also interesting to notice that these things are becoming so widespread that they're finding their way into the standard libraries. Okay, now the immutable collections.NET are designed with the goal to also reuse memory, as much memory as possible, so that we don't have to copy structures all the time, to have structures that are thread safe, that can be shared safely, and that do not cause a lot of extra pressure on the garbage collector. So very nice, and immutable collections support roughly the same operations offered by their mutable counterparts. These collections reside, so let me actually call them up in the system.collections.immutable namespace. There we go. And in here, well, we have a bunch of collections that are similar to the mutable ones we've already seen. So, for example, list prefixed by the name immutable. let me show. Let's say that we want to create an immutable list. There we go. Well, there's an immutable array, for example. But let's say we have an immutable list of int, and actually, interestingly enough, we just start with the empty collection. Okay. How do we add things to something that's immutable? Well, the collection itself is immutable. So this empty collection that IL is referring to is going to be empty forever. It cannot be changed, it cannot be mutated. But the variable IL is not a constant. The variable itself can shift. So the collection, if someone else in another part of the program is referencing it, it's not going to change, but IL can shift to a new collection that might reuse or extend the original empty collection. So I can say IL.add, let's say I add 0, and this returns a new collection. So by doing IL is IL.add, this IL remains empty. To empty we add 0, so now we create a collection which is 0 at the start and empty following. And this new collection is referenced to by the IL variable. So the IL variable itself is mutable, but not the underlying collections. Because IL.add returns an immutable list, I can also say add 0, add 1, add 2. I can chain these things, and this will create, well, first we have created or referenced, because this is sort of a singleton if we want, so it's always the same, the empty collection. This creates the collection empty plus 0. This creates the collection 1 plus empty plus 0, and so on. So this creates a bunch of collections, but the funny thing is that the remaining collection that we have here in IL refers all of those temporary collections. So we didn't create a copy, we just refer to them because they are immutable, so we can safely refer to them. Let me take a look at what the debugger shows. With a little bit of luck, we might get to see a hint of this. But in good likelihood we won't be able to see it. No, this, okay, let's see. So on one hand it's showing very neatly that there is 0, 1 and 2. Yes, very good. But yes, okay, this might be it. So we have the root, and you can see that, okay, there's left and right. Oh, fascinating. So the root is 1, and the node to the left contains 0, and the node to the right contains 2. Very beautiful. So this is sort of suggesting, and you can see that the node to the right has nothing left, so because is empty is true. So you can see this is a very sophisticated dynamic structure of all of these intermediate collections that we created, which are just referencing each other. And also, funnily enough, what it looks like, this immutable list underneath has more of a tree structure than a list structure for extra flexibility, because when you have a tree, you can actually extend wherever you want. There's plenty of immutable containers. I'm not going to look into all of them, of course. Just know that we can use them, minus this. So this you will see all over the place when dealing with the immutable collections, that you have to reassign the variable pointing to them, but for the rest, these immutable collections just behave exactly as you would expect them to behave if they were not immutable. Well, the immutability doesn't really have any other impact in the normal use case scenarios. We can go through them. Then, well, we can run link queries on them. So let me show. This we're going to look at later on, but we can filter all the elements. So you could say, okay, give me all the elements that are even, and now we will get only 0 and 2. On IL we have remove, clear, and of course anything that suggests a change of the collection will not change the collection. So if we want to remove something, what we get back is a new collection with references to parts of the previous one where the operation has been performed, but the original one is not changed. We have stuff like find all, find index, etc. So and we also have the square bracket operator, of course, which simply looks up the element at index 1. So very cool, just the same, but you can share your collection, knowing that it will never change unexpectedly. So that's actually pretty nice. We also have immutable dictionaries. So yeah, let's say that we have a house data structure and it has an ID. And yeah, whatever, it just has a name of the house. Okay, not very exciting. And then we create our dictionary of houses. And this will be an immutable dictionary. You can see plenty of things, by the way: immutable array, dictionary, hash set, queue, sorted dictionary, sorted set, so many things. Okay, we will see them in the algorithms and data structures course. Okay, so immutable dictionary of GUID and house. And this one also starts out as empty. And whenever we want to add a house, we will have to say houses is equal to houses dot add, and then we can add, well, the GUID and the house. Let's create a little function to do this. Add house takes as input the new house to add. And the reason why I want to add houses like this is that I then get to reuse the ID like this. Let's see, why is it unhappy? Oh, because it thinks that this is a possibly null reference. It's actually quite unfortunate. So let's fix this with a more proper declaration stating that no, this is not going to be empty. And now, because otherwise I have to pass the same GUID twice, and that's actually annoying. So here I can say add house, and then I can just create the new house, GUID.new GUID, and then I don't know, family resida, family maggiore, family Singh, family van Haren, and so on, and so on. All right. So also, once again, if we only called houses.add, this would result in nothing whatsoever. The houses dictionary would still point to the empty dictionary, nothing would change, nothing would happen. So we always need to reassign the houses variable. And now we can also, of course, go through all the elements of the dictionary. So for each house in houses, and house will actually contain the value and the key, because, as always, being a dictionary, the entries are the pair of the key and the value put together. And so here we could just print out console.writeLine, and then let's print a slightly prettier house.key is equal to, yeah, whatever, and then just a house.value, and then the ID we've printed already, so we just print the name. Let's run this. And there you go, we have the IDs and then just the name of the house. Not super exciting, but yeah. And let's say that one of the IDs we saved. There we go. Now we could also perform the usual lookups. So houses of ID. In this case, we are pretty certain that there is going to be an insertion. So what we get is what we're going to get is this house here. Of course, this is not a key value pair. This is just the house itself. We just looked it up, so we have the ID and the name directly. And we can run this, and we are going to get, well, obviously the correct combination. Now this might not be there, of course, in general, so we have to be very careful to make sure that indeed. Oh, and by the way, the type reflects this pretty neatly by saying that this is a house question mark, so we should always check whether or not the house was actually available. And actually, if we try to fetch something, well, we'll get a null reference exception probably. Oh no, we do. Oh, we do get the same kind of error which says, okay, the given key was not present in the dictionary. So we don't get null, but rather we are supposed to first check if houses contains key and then ID. And if that is the case, then we can safely fetch or look up the element. Otherwise, we will run into an exception. Okay, very good. Immutable dictionaries are actually used in practice quite a lot whenever we want to, for example, simulate and control something that resembled shared mutable references, but where we need to have control over when are things committed to the storage by reassigning the variables. And yeah, also in general, dictionaries themselves are excellent to have quick access by ID. So the example I've shown, this is one I've actually seen many times in practice, especially when you have interconnected structures or structures referencing each other without repetition. Then immutable dictionaries are very powerful. So let's say that you have people and you have houses and you want to model the fact that people live in houses, then you could have a structure like this. I'm not going to complete the full type definition of person and house, just for your intuition. Then we could have the houses, we could have the people. But how do you model the fact that people live in houses? Well, whatever, let's accept the nullness, we don't care. You could define a lives at relationship which connects the GUID of a person to the GUID of a house, for example. Or you could say, no, this is not the GUID of a house, there's a bunch of GUIDs of a house, but because, well, a person lives in a set of houses, so without repetition, we could actually make it a hash set. And this actually simulates something that's very close to a relational database, which allows access by ID very quickly. So this is again a pattern that you might encounter in practice, actually pretty much.